Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresh Wen University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon, everyone here in this room and everyone online. Welcome to the IF Colloquium. And today we have an honor to welcome Dr. Chakrit. Chakrit, sorry, Dr. Chakrit Pongkitivanichkul from Khon University. And today he will tell us about introduction to Axion Like Particles. Please welcome our speaker.
Thank you. Can you hear me? Okay, yes. Good. Thanks for inviting me to give a talk here. It's always my honor to, give a talk at EVE. I always have fun, and I wish to go back there soon. Yeah. So today I would like to talk a little bit about the topic that is close to my heart, because I keep working on it basically all my life now. It's called the Axion Like Particles, or the ALP, or you can call Axion if you like. The talk that I would like to give today is more like a kind of a basic level. If if you're a student or grad student, you can follow along and try to ask some questions, and I will try to answer as best as I can. So basically, today what I want to talk about is basically a mixtape of Axion Like Particles. So it's my favorite topics that I would like to put in. It's not like the cover of every topics that you can think of about Axion Like Particles, because that's a lot. And it's so big now because you have a lot of experiment, you have a lot of theoretical development on Axion. So I'm not going to promise you that I can cover all of them, but I'll try. Okay. You see my next slide, right? Okay. So basically I would like to start the talk by putting some names in, right? So that's Steven Weinberg, one of my favorite physicists. One of his monumental paper called the cosmological constant problem, which is the first one that raised the problem about the mismatch between the quantum field theory and cosmology and stuff like that. So the opening line, I love it very much. Physics thrives on crisis. So basically, if you think back about the progress that we have made along the line of physics like 400 years ago, right? Everything is made after the crisis. So basically, you have to think about the problem first, right? And that problem is lacking of something, and then you have to solve that in a way that gives you a new progress in physics, right? So one of the example that I think the prime example in this paper is the cosmological constant problem, which I'm not going to talk about. I think you guys know all about this, no? But right now, I don't think crisis is a bit overkill. I would say problem now, because it's, you know, we have a lot of clues, we have a lot of, you know, precision measurement and stuff like that. So basically, this is how we progress in physics. We start with a problem that kind of inconsistent in some way, and we have to, you know, solve it, and that's the way to progress it. I don't think the word, the sentence, unfortunately, we have run short of crisis lately, is true, because in Weinsberg context, he's talked about the big one, right? So we still have a lot of stuff that we cannot explain, like dark matter, dark energy, and stuff like that. Yeah, so that's the main goal of this talk. I would like to say what is the problem and what is the way forward in terms of the progress in physics, right? So yeah, obviously we have to talk about symmetry. Symmetry in physics is kind of a hand-to-hand topic now, right? Because this is one of the most beautiful concepts in physics. So basically, every physical law that you can think of, there's always a symmetry behind it. And instead of talking about the physical laws, we can just talk about symmetry now, basically, right? So that's the quote that we usually say is that symmetry dictates how physical law should look like. So that's journalists try to look at the physical law using its symmetry, right? So that's basically the goal of the game for physics now. And I would argue the other way as well, right? On the flip side, instead of having only symmetry, it's not enough, right? So we know that the world is messy, the nature is also messy, right? We have a lot of stuff that is break, right? And that's just broken, right? So the symmetry breaking is also as important as the symmetry itself. So on the flip side, you can talk about the Madame Wu's experiment, the parity breaking weak interaction, or also the most important one, right? The Higgs mechanism, which is the symmetry breaking as a prime example, okay? So since the main topic here is a symmetry, so I would like to start with a simple one, right? So let's think about the symmetry in the mirror. So this is called parity. So when you do the parity action or the parity transformation on something, right? So you just flip the space side, not the time side. So if you have a vector, you flip a vector, okay? And if you try to separate into the world or the world of physics into two quantities, you would have a negative parity and a plus parity, right? And minus and plus. So the usual one that you can think of is just a vector, right? The x is a minus negative parity. Velocity should be a negative parity. The acceleration should be negative parity. The force should be negative parity, right? And the electric field should be negative parity because the force, right? And if you try to think about the plus side of the parity or the positive parity, if you have two vectors here, right? For example, x and v, you would get that the angular momentum is positive. And if you take f as a negative parity, and v as a negative parity, b is a positive parity. And since b is a positive parity, then you get the gauge field or the vector potential A here as a negative parity, because this nabla here is a vector as well. So you have a negative parity for the gauge field on the space side. For the potential one, you should get plus parity, right? And for the current charge, right? So the rho here, which I write in terms of the current, the current of the fermion, this one is supposed to be the positive parity as well. And the vector side is a negative parity, right? And the most important one is the one that has a pseudo-scalar stuff, gamma 5 in here, right? So the gamma 5 here, the purpose of having gamma 5 here is just flip everything. And that means instead of having a negative parity for the vector side of the current, you would get a positive parity here. For the rho, you would get the negative parity. So this is one of the examples that we can try to give for the parity symmetry of the system. Let's do another one. Okay, so we can talk about the flip in the charge. It could be any quantum charge that you can think of, but now just focus on the EM, right? So if you try to flip the quantum charge, right? So let's say electric charge, you flip from the negatives to positive. So if you try to separate the quantity into two categories again, you have positive plus, the positive C conjugation and negative C conjugation. And the obvious one that should be the charge, right? Q, that has to be negative. Otherwise, you wouldn't flip it, no? And the electric field as well, and the magnetic field as well, right? So in this case, if you have a force here, right? Since force is a positive one, right? And V is a positive, right? B is supposed to be a negative, and E is supposed to be a negative as well. And that includes the gauge field for A as a vector side, and also the scalar side as well, right? And that also includes the charge, the current charge, the current for the fermion charge, right? And the gamma 5 is also the positive C conjugation. So we can play this game all along, right? And we can think about the combination of charge and parity symmetry. And it turns out that the CP symmetry, so-called, is also a matter-antimatter symmetry. For example, if you have an electron, right? If you do the C symmetry plus P symmetry, you get a positron. That's basically the game that we want to play here. And since we know all the quantities, the charge quantities of every, the charge property of every quantity we have now, we can just try to check whether or not our usual stuff like QED, electrodynamics, respect C and P, right? So if you try to write the Lagrangian for the EM, right? So for example, the kinetic part and also the current coupled with the gauge field stuff, right? You can write in terms of the electric field and magnetic field, you get E squared plus B squared. And if you go back and try to, keep track of all the charge of C and P for E and B, right? You see that E squared, no matter what you put C and P in, is always invariant, right? B also, right? If you put minus here, plus here, you get square, you get the same stuff. And this one is a little bit tricky, right? Because you have to separate into two parts, the time component part and the space part. For the time component, you can think about this, right? So the rho would contract with the A0 here. So you have negative and negative, that is positive. So it's invariant, right? For the vector part, you have negative and negative. That is also invariant. So therefore, the whole QED is C invariant. So it's respect C symmetry. The same goes for P symmetry, right? Because if you try to match up with this and this, right? So rho and A0, that would be plus and plus. That would be plus as well. And J vector dot with A vector, that would be minus and minus. That would be invariant as well. And of course, CP, or the combination of C and P, must be the symmetry of the system as well, right? Because it's just a simple product and you can transform it separately. So this is a prime example of having a CP symmetry in the theory, right? Can we do something a little better? Like, for example, we can think about the theory that is violate C and P, but respect CP, right? So obviously we have one of the stuff that we use a lot, right? It's called the axial vector current theory. And this is going to appear in the standard model and all the stuff that you think of, right? This structure of the theory is interaction of the vector and the gauge field and the axial vector, which includes the gamma 5 and the gauge field. So basically you have two parts, right? The vector couples with gauge field minus the axial vector couples with gauge field. Now we have to include the axial part into the game, right? So in this case, if you think about C symmetry, right? So you have to match between the time component part for these two. So you have this and this, right? So the negative and negative, you get positive, which is cool. For C, for the vector part, you have negative and negative as well. So the vector side is always respect the symmetry, which is good, right? Because we actually check it. No, the same goes for the P, right? For the first part, you get plus and plus. You have minus and minus. That would be the invariant as well. So V is an invariant. V is an invariant. Sorry, the invariant quantity in the V in the CP symmetry. How about the axial part, right? So if you think about the axial part, you have, where did I put it? Here, right? So this, no? So the time component of the axial part, you have plus times minus, right? So you get minus sign here. And for the vector side, you have plus times minus. You
May
get
I
minus
interrupt?
sign here. Yeah.
Chakrit, we didn't see your pointer actually.
Really?
You
How
can tell more about when you point.
how do I do it in here?
You have to say more actually.
Shit. Let me see. Do we have any like tools that we can use? No. Huh.
We can.
Sorry. So
We can
wow.
have. Can you explain in a little bit more detail?
Okay. Now, okay, I got it. So it's it's a little challenging now. Right. So, but you get the last page, right? It's okay, no? You can keep track, no? Okay. Okay.
Yeah.
Right. How do I do this? Let's go slowly, right? Okay. So the vector part of the V minus A theory is always conserved for C and P. That's fine, right? For the axial part, you have to separate into two parts, the time component and the vector component, okay? For the time component, you would get plus and minus. So that would be a minus sign, right? For both the time part and the space part of the axial current, right? For C symmetry. For P symmetry, right? You also get minus times plus and plus times minus for the axial part as well. So under C and under P, the axial part gains a minus sign. Okay. So therefore, if you try to think about C and P, so it respects the CP symmetry. Okay. So in this case, you would say that the axial current actually breaks C and P separately, but it respects CP symmetry. I think yeah. So I think I try to explain it slower, right? And try not to point things around. Okay. Yeah. Yeah. Sorry about that. So I thought you see my, okay. If there's any way I can do it, that's going to be better. But okay, right now I think we can carry on and try to, I'll try to explain slower and without using the pointer. Okay. Okay, that's good. So we now know that V minus A theory respects CP symmetry, right? How about putting into the actual action or the actual Lagrangian? So we now know that, right, the weak interaction violates P symmetry like badly. That's Madame Wu experiment long time ago. We can try to write the Lagrangian for the weak interaction as well using the V minus A form. So instead of having the just a one type like this one type of fermion, we now have a up quark and down quark and W boson as the interaction. So this is the weak interaction, okay? So if you do the CP transformation here, right? So if you do the CP transformation, what you get is that you have a flip in terms of the field because of the phase rotation in front of the CP transformation. So the V minus A form really respect the CP transformation, the CP symmetry. So you can just turn it around and everything will be equal, right? Except that the requirement for the weak interaction theory is that the part with the Vij star here, which is coming from the CKM matrix. This is the part where you have a rotation on the flavor space, and you get extra matrix structure inside of the U quark and D quarks. And if you look at it, right, so the theory looks like it respects the CP transformation, the CP symmetry, if the Vij star is equal to Vij. It looks fine, right? I mean, that's a solid assumption that we can make, right? So we can think that, okay, CP symmetry is a symmetry in the weak interaction. But it turns out that it's not really, right? Because the nature is kind of mean to us, right? The nature choose not the easy way for us, because these two phases are not equal, right? So the Vij and Vij star are not equal. It means that the CKM matrix has a phase inside, has a component of the phase, the imaginary part inside. And how do we know that, right? So we actually first observed in the system of the Kaen oscillation. So there are two types of Kaen. So that's meson. We have D quark and strange quark. If you write in this way, right, you would have oscillation between K0 and K0 bar, and K0 to K0. So the transition rate between K0 to K0 bar and K0 bar to K0 depends on the phase, right? So one of them would be V star, V star, and one of them would be V star V star V. This one has a difference in phase. And if you try to do the linear combination, because this K0 and K0 bar is not a mass eigenstate, the mass eigenstate is a Ks and Kl, which is a linear combination of these two. You will see that the experiment shows us that you have the Kaen decays into two pions, which violates the CP symmetry, because the parity of the Ks, or the K short, is -1, and pi 0 has a parity of -1 as well. So the one Kaen decays into two pions. That violates P symmetry, which is originated from the fact that the CKM matrix has a complex phase. And this might be a little off, because we think that the CP symmetry should be the symmetry of the nature, right? But not really, right? Because if you think about it, CP symmetry is a matter and antimatter symmetry. If you go back into the first second of the universe, there should be some kind of asymmetry between the matter and antimatter. Otherwise, you wouldn't have a lot of matter around us, no? So this could be a part of the origin of everything around us, because we have seen a lot of matter, not a lot of antimatter. And this is good. So this is a prime example of using a CP violation in explaining the nature. And the nature choose to break CP, right? How about the strong interaction? For the QCD, things get a little messier, right? So we have a source of CP violation, and one of them is called the instanton effect. What is the instanton? It's basically, if you try to minimize a theory, you have a non-trivial configuration, and that contributes to the Lagrangian, right? And the one that we typically write in terms of the instanton action of the gauge field is in terms of G and G tilde, which is the dual of the gauge, the field strength tensor of the gauge field. And G here is the field strength tensor of the gluons, okay? And this thing is a CP violation term. Why do I say that? If you try to write the same thing in the QED, yeah, you write F mu nu and F mu nu tilde. And if you write that in terms of E and B, you get E times B. And what's E times B? It's CP violation, right? Because E is negative in C and negative in P. B is negative in C and positive in P. Therefore, if you try to do the CP transformation, you will get plus times minus. Therefore, this term violates CP symmetry. Okay, and the zeta term is kind of a free parameter that you can give for the instanton solution, because It can be anything, right? So it's we never know that after symmetry breaking, after the universe happens, then zeta just falls into one of the values that are allowed. But that is not the only way that you can introduce CP violation to this strong interaction. Another way that we can use is the chiral anomaly. So basically, some symmetry is not a symmetry at the quantum level. For example, the one that we typically talk about is the chiral rotation. So chiral rotation for the field theory is a symmetry in the massless limit, right? For example, if you try to rotate the left-handed quark fields one way and rotate the left-handed quark field another way, you would get that the current, the axial current, the Noether current is non-zero with the mass not equal to 0. And what happens is that if we try to calculate the expectation value of A with the pseudo-scalar part of psi bar gamma 5 psi, this is equivalent to the diagram above. So in the QED, right, this thing is called triangle diagram for pions. The calculation is pretty messy. So I'm not gonna try to give you some some insight on this thing. But the bottom line is that after you calculate this, right, you would get F mu nu and F mu nu tilde, which is exactly the same as the CP violation that you can introduce through the instanton. Okay. And what does it mean by the expectation value of the gauge field to the pseudo-scalar part? It's basically try to think about the quantum level of the interaction. So if you use the Noether current for the axial current, you would get that the Noether current is not 0 at the quantum level if you think about the background gauge field as a vacuum. So in this sense, the symmetry is broken by the fact that you have the chiral rotation, and the term that you can use is exactly the same form as the CP violation that you can introduce from the instanton. So the bottom line is that the Noether current is not conserved at the quantum level. And how do they do that? If you try to do that, what you get is that the Lagrangian would add another phase rotation, alpha, times this violation of the Noether current, d mu j mu 5. And if you combine that with the instanton, right, and if you can do it freely, you can think about zeta term or the instanton term as a non-physical, right? Because you can choose alpha as large as we want. You can get rid of zeta. That's it, right? So everything here that I just talked in the few slides back then is just meaningless, right? You can just always rotate it away. But that's not the true story, because the fact that quarks are not massless, right? Because since quarks has a mass, the chiral rotation is not free. After you do the rotation of the quark, the left-handed and right-handed quark, you introduce some phase into the mass matrix. And the mass matrix there would enter to the CKM, and it would enter back into the CP violation phase as the alpha one here. So in a sense, whether or not you try to rotate away using the chiral anomaly to get rid of zeta bar, the zeta term or the instanton term, you always come back to some CP violation phase anyway. So the chiral rotation doesn't work if the quark has a mass, right? And we know for sure that quark has mass, right? So that thing is a no-go. Therefore, actually, zeta term that we are talking about, or the strong CP violation phase, is physical, and you can measure it, and we cannot rotate it away. So it's real. You have to measure it. The point is, we actually measured it, and we didn't see anything. Yeah. So the best limit that you can try to measure it is coming from the neutron electric dipole moment from this diagram, for example. You have a neutron, right? And you have a similar triangle diagram with the photon. And this is the electric dipole moment equivalent in terms of the Feynman diagram. what we actually see is that the value of the neutron electric dipole moment is very, very low. Like currently, I think it's around 10 to the minus 26 electron times centimeter. And that thing, you can calculate it using the CP violation phase theta bar here. What you will get is that the theta bar here is around the order of 10 to the minus 10, which is extremely small, right? And the problem is this: there's nothing that you can tell. We can tell that theta should be at around 10 to the minus 10. If anything, it should be of order 1, right? So this is a dimensionless parameter. If anything, you expect the order 1 parameter, like 0.1, basically, right? And this is bad, no? And the fact that the expectation from the theory and the reality of the experiment doesn't match is basically telling us this is a real problem. And this is called the strong CP problem. And this is one of the main motivation of the introduction of the axion, right? So what are the solutions? The first one that comes is coming from Ph.D. and Khon, right? So what do? They actually just add a chiral U1, okay? You have another U1 that add in, okay? And you think that it should be anomalous, right? So because a chiral U1 has a mass and stuff like that, you generate another term and try to get rid of it. That's basically the idea, no? But if you try to think about it, it's clearly not in the standard model at all for the extra chiral U1 that you can think of. For example, if you think about the standard model Higgs sector, okay? And if you assign the new U1, I will call U1 PQ, okay, as a phase rotation of the left-handed and right-handed quarks, okay, with a different phase, you see that the structure of the Lagrangian doesn't respect this symmetry at all, because from the left-hand side, you expect Higgs to rotate with the phase 2 beta, but on the right-hand side, you expect Higgs to rotate with the phase minus 2 beta, which is wrong. So you have to do something about it, right? And this is why we need a new theory or a new part of the theory that you can add in. So we need a beyond standard model theory for solving the strong CP problem. And the obvious one, right? If you have a mismatch between these Higgs charges, just add another doublet. And it's more common than you think, I think. So the model that I'm talking about is a 2 Higgs doublet model. And this is a big class of the model. It includes SUSY and stuff like that. But right now, just focus on the typical 2 Higgs doublet model with the chiral U1 PQ. And if you try to do chiral U1 transformation on up quark left-handed, up quark right-handed, down quark left-handed, down quark right-handed, you see that H1 and H2, which is the Higgs doublet 1, Higgs doublet 2, you can call Higgs up and Higgs down, that's fine, would rotate with a different phase. And that's good, right? We can just add in. And if we try to tie in the PQ charge with the Higgs field here, and you can see that U1 PQ is spontaneously broken by Higgs wave, okay? And as you all know, if you have a spontaneous symmetry breaking, you always get an extra scalar field. It's called Nambu-Goldstone boson. In this case, for the U1 PQ symmetry, it's called axion. And we use this axion to solve the strong CP problem. Why? We can use the chiral rotation, right? Because if this is the axion, no? It's basically the phase in the quark mass phase. Yeah. After Higgs gets swept, everything, you're gonna get the quark mass phase in the, the Yugova metric and stuff like that. So basically, you can do the chiral rotation using U1 PQ to get rid of axion, and it's gonna appear into the CP violation phase. So basically, we get rid of A, right, which is a field. We add it back into the CP violation phase here. So you have theta bar minus A, which is a field, divided by the symmetry breaking scale V. And that is the effective theta parameter for the Axion model. So this is nice because we can try to solve the strong CP problem using the dynamics of the Axion field. We can try to calculate its vacuum energy. So in this case, we can use a chiral Lagrangian, and the vacuum energy is basically tied with the pion, because in terms of the chiral Lagrangian, pion, axion, and all the pseudo-scalar stuff is in the same doublet, right? In the same, in the same category, and you get mixed. And in this case, you would have a cosine potential, or the cosine vacuum energy. And if you try to minimize it, like go down to the lowest level of the energy, you will see the zeta bar vanishes, because the A would drive everything into the minimum of the energy. So A at the minimum should be the vacuum expectation value of Higgs multiplied by the zeta bar. Therefore, the effective zeta bar is 0. Therefore, we solve the strong CP problem. So this is the main motivation of using the Axion to solve a strong CP problem. Basically, if you add more stuff, right, add a U1PQ and let the symmetry of the U1PQ break at some scale, you will introduce Axion. And after you introduce Axion, it would get rid of the CP phase for you for the dynamical reason, as I showed you here. And the most important point about this is that if you expand A around the minimum, the energy here would give the mass of the axion, and the mass of the axion would relate it to the pion mass, like this, with the electroweak symmetry breaking scale, MA equal to M pi multiplied by the constant, the decay constant of the pion, divided by the electroweak breaking scale V. So you have some kind of relation between mass and V, yeah? And unfortunately, this model is called Pesci-Quinn-Weinberg-Wilczek model. It's ruled out pretty quickly. Like after a few years, people realize that this is not a good model. The reason is that if you use this interaction here, you will see that the strength of the interaction would depend on 1 over F or 1 over V here, right? And the energy loss would be too large for the axion radiation inside the stellar system. I will come back into this point and talk about the experimental limits later. But the point is that you have a constraint coming from the energy loss of this the star stuff, and it contradicts with the electroweak symmetry breaking scale V. So we have a lot of ways to go forward, right? So if that doesn't work, the obvious way to go is to decouple the electroweak breaking scale from the p-key breaking scale. The easiest one that you can think of is just add another scalar, as we usually do, right? And we add the complex scalar here, S, and let it gains the expectation value. So it's break symmetry, right? And you assume that the singlet complex scalar is charged under U1PQ, and it's the same game, right? So you have the Nabucco boson as an axion, and this one would be different because the breaking scale of the complex scalar is Fa now, which is not the same as the electroweak breaking scale, like last slide, right? So Fa now you can write in terms of the expectation value of the scalar S, and Vs can be large. You can put some arbitrary large number, and you get a large coupling Fa, the coupling constant Fa. You can suppress the interaction between axion and all ortho standard model particles, and this is somehow we call just the invisible axion, because you don't actually see it right now, but we have a potential to see it later, just to avoid the constraint. Okay, so this is a DFSAT model. This is one of the common canonical type of the axion model. Another one is less common, but it's okay. So you have to decouple p-key breaking scale by adding a new scalar and also adding a new heavy quark Q prime. And if you do that, and you assume that the U1PQ, the new U1PQ, is assigned to only two new fields, scalar singlet and heavy quarks. In this case, you get the same story. You have to decouple. You have decoupled the PQ breaking scale with the electroweak breaking scale completely, so it doesn't have anything to do with each other. So it's also called the invisible axion as well. But this model is less popular because it's pretty hard to see it, right? Because you don't give any PQ charge to the standard model field, and therefore there's no tree-level coupling to quarks and leptons with the axion at all. So this is like invisible axion, the real invisible axion now. So these are two models that are kind of a canonical type of the axion model. We have another one, right? So that's the one that I usually talk about. It's a string axion. So you have another theory of this string, of another version of the axion stuff is coming from string and M theory. So as you all know, right, string is the extra dimension theories, and you need to connect with the real world somehow, and that process is called compactification. So it's basically the mathematical process to reduce the number of dimension into 4D. And obviously there are a number of scalars coming from that stuff, right? For example, if you talk about the metric side, you would have the stuff called moduli, or the stuff, the parameter that controls the size and the shape of the hidden manifold. And you would get a scalar field called moduli fields. Also, you would get the p-form field, the gauge field in the extra dimension. And that could also give a number of pseudo-scalar particles called Axion Like Particles, or ALPs now, right? The reason why we call Axion Like Particles is that these Axion Like Particles are not necessarily axion that we used to have in the strong CP problem. So in this ALP stuff, you don't need to solve strong CP problem at all. I mean, it doesn't have to, right? So you can just assume some string theory stuff and extra stuff that put into the theory. So this is why people call it axion-like particles instead of just axion. And the thing is, these axion are coming with a large number. Since typical gauge field or the p-form field is expanded on the p cycle on the topological space, and these numbers can be large, right? So I used Kruger-Skark list from this paper, right? And if you try to do the frequency analysis of the number of the topological number, it is called Betti number, and you see that you expect to see at least the most common one would be around 30 fields, the 30 pseudo-scalar fields. And this is the original story of why people say the string theory predicts a large number of ALPs, because the common stuff for the hidden manifold, for example, Calabi-Yau example here, produce a lot of Betti number, produce a large number of Betti numbers, and that introduce a lot of axion into the string theory. And that is good, right? Because we have a lot to play. Especially if you think about the superpotential stuff and derive the mass of the axion, the mass of the axion would be suppressed by the instanton action S instanton. And that could be large, right? And it could be many order of magnitude separated. So therefore, if you use the axion that coming from the string theory, people typically expect that the ALPs are generically light. So like in the order of like 10 to the minus 20 EV at least, right? And could span many order of magnitudes, like from minus 20 to 10 to the minus 32 EV, for example. And that provides you with a lot of playing ground for the phenomenology, ranging from a large axion, the heavy axion, right, to the left end of the spectrum is the lowest mass of the axion. And we have a lot of stuff to constrain with, right? So you can use axion to constrain from the experiment. You can use axion to constrain from the astrophysics. You can use axion to constrain from cosmology as well. And that is what I want to talk about today, okay? Basically, there are lots of stuff that we can try to think of and try to constrain. and it's good, right? So I would try to separate them into 3 categories. One is the lab search. Second one is the astrophysics source, which we can observe. And the third one is the observation from the cosmology, called cosmic axions. Let's talk about the general plan first, right? So what are the general stuff that you can think of about the axion interactions? So axion can interact with photons, yeah? And that could come from the anomaly term that we just write. And that thing is simple. So you have axion, right? And then the topological term for the gauge field, F mu nu tilde. And the coupling there in front of them is GA gamma gamma, which we can detect. And if you write F mu nu and F mu nu tilde in terms of E and B, that would be E, B, and axion. Okay, so that's the axion photon interaction for you. For the fermion stuff, right, is highly model dependent. As I said, right, you can give PQ charge anywhere you like, but generally you expect to see the kind of derivative interaction with axion with the pseudo-scalar part of the fermion there. Also, some people also write this term, right, in terms of after you do the Fourier transform, you get the M of the fermion in front, and you get a pseudo-scalar version of the interaction between axion and fermions. And the main thing that you can try to constrain is coming from the Primakov process. So you can do the axion photon conversion under the presence of the heavy nuclei, like this diagram. So you have a heavy nuclei, you have some electric field or the potential or the photon, and you can interact it with the photon and axion. So you convert from photon to axion under the nuclei potential. So let's talk about the first one, right? We can think about the constraint using the lab search. And the first lab search is kind of cute, right? So you emit some photon, okay? And you use the strong magnetic field, like this one. We have the interaction between E, B, and phi, right? So if you use the strong magnetic field, you can convert from photon to axion easily. And if you put the kind of a concrete between the source and the detector, so basically you have a walls between the source and the detector, you can convert it using the magnetic field and convert photon into axion, then axion propagates into the walls and coming back and turn it back into the photon, and then you detect it. So this is a cute experiment called shining light through walls, because light cannot pass through walls, right? But axion can, because it has a weak interaction. So these are the current experiment that gives the current base limit, called Oscar, ALP2, and also Krauss at CERN. You have another limit from photon polarization, right? Because you have the interaction between axion and photon. And if you put E, right? If you put a beam of light or just some EM wave, right, under the magnetic field in the transverse magnetic field like this one, you would have the axion photon interaction between the magnetic field and the electric field. You would kind of expect to see the polarization of the E field to be tilted a bit toward the end. So you can detect that kind of tilting of the polarization due to the axion photon conversion. And this is the experiment called PV-LAS, right, in Italy. So that's one of the way that we can try to constrain. And the major one, I think, the one that we expect to see like pretty easily is the one that you can think about in the astrophysics, because axions, if you use those interaction, right, axion can be produced in the hot plasma in the stellar fusion process. And since if axion is produced inside the star, and axion is weakly interacting, so it can travel out of the star and carrying along the energy, carrying along the momentum. Therefore, the fuel or the nuclear fusion process would run out quickly if you have the axion. So you expect that the if you try to use the solar, the solar model and the stellar model life cycle, you will see that if axion exists, you should have the shorter lifetime for these stars. So you have some constraint from, for example, horizontal branch stars, red giant, white dwarf, or neutron star as well. And some people say that you can expect to see some difference in the supernova as well. Another one, you can think about the axion that coming from the sun. Okay, so suppose that axion comes from the sun, and if you point the detector toward the sun, but you block it with some concrete wall and use the magnetic field, the strong magnetic field, to convert axion from the sun into the photon, and you observe it, right? You can put some constraint into the axion coming from the sun as well. And this is a current experiment called CAST, the Axion Solar Telescope. And the bigger one that is building is IAXO, International Axion Observatory. So we also have another one from the astrophysics side. This is super interesting for me because I used to work on it a bit. It's called super radiance. Basically, a lot of people find that if you have the field, the axion field, or just a pseudo-scalar field, actually, with the wavelength comparable to the black hole size, right? So the state of the axion would bounce, black hole size. So axion and black holes would bounce states around the black hole. And the occupation number would extract the angular momentum and the energy out of the black holes. And you can see that the spin of the black hole would get slower if you have the axion at that size, okay? And you would expect to see also the gravitational wave coming out from the energy that the axion extract from the black holes as well. So you can put some limit on the observation of the spin of the black holes and also the mass of the black hole as well. So this is one of the constraints that we can have after observe or the approximate the spin of the some supermassive black holes. You have another side of the axion as well, coming from the cosmology. So if you try to analyze the axion field, right, in the expanding background, you will get this kind of equation. So it looks kind of like a particle, except the middle term called the Hubble friction term. And if you have the Hubble friction comparable to the mass of the axion, which is the last term, dV by d phi, you will start to see some oscillation in the field. And that's basically the main mechanism of producing the axion as a dark matter. So if you imagine the plot on the right? So you have the axion field that is frozen in time at the early universe, right? And as the universe expands, right, the Hubble scale would get lower after the Hubble scale crosses with the mass of the axion, the top right panel here, right? So the Hubble scale gets down below the mass of the axion, so the friction would be gone, and therefore the axion would start to oscillate around its minimum. And the oscillation of the axion around its minimum is basically the Klein-Gordon equation, and that produce a dark matter from the axion. So if you try to play this game, you can try to constrain it as well, whether or not you can have an axion as a dark matter or dark energy, because axion field that is frozen in the space is also contribute a lot of energy into the space-time. So that would be also a dark energy as well. You can have the axion that is produced from the decay of the topological edge defect as well. Like, for example, we have introduced U1PQ, right? So the U1PQ itself should have some kind of a topological defect, like domain wall, cosmic string, and stuff like that. And that decay would produce a lot of axion as well. And we should be able to see them if it exists. Okay. You have another interesting physics as well. If you have the axion that is pairing up with the moduli field that is basically coming from the string theory. So you can play a lot of interesting physics with moduli and axion, because moduli, as it happens, it gets mass from somewhere else and it's heavier. So it would become quickly coherent and becomes a mass earlier than the axion. And as the universe expands, the moduli would get decay into the axion field, and that produce a lot of energy into the thermal bath of the universe. And we can try to see or try to constrain the effect of the moduli and moduli decay into axion in terms of the effective number of neutrinos as well. And this is called dark radiation. Okay. So I think I'm on time, which is good. That's my introduction of the axion. Okay. Basically, right, if you go back, axion is originally proposed as a solution of the strong CP problem, right? And this basically leads to the need for the BSM, for the beyond standard model theory, and other solutions as well. For example, string theory, which predicts a large number of ALPs. And that's good because we can do a business on the axion caching stuff, right? I actually found it. It's actually the brand name of the detergent. So it's kind of a huge breakdown for the theorists and experimentalists as well. So that's my conclusion. And if you want to learn more, obviously, yeah, you can contact me or my colleague Jandarit at the Khon University. And that's it.
Okay, thank you very much. Is there any questions here or the audience online?
Okay, may I ask some?
Yeah.
Can you apply the axion field to die the inflations?
Oh yeah. Yeah, I forgot to put that in. It's not my main field of expert, but yeah, I mean that's just typically what people do, the axion inflation. But generally, I think one of the main problem they have is the decay constant. So the decay constant, typically, if you expect from the axion, for the axion inflation, the decay constant would go over the Planck scale. So that would be a no-go for me if you try to think about the axion inflation, because that means that the U1PQ breaking scale is higher than the Planck scale. So something fishy is going on here, right? So that's why people don't actually use just axion inflation. There are some interesting ideas, but I mean, we can talk about it later, but people use a collective phenomena of axion to reduce that F number down. There's some like inflaton, something like that, inflation. Yeah, so that's a main way to do the inflation in the axion system. Yeah, I guess you are interested in inflation, right?
Yeah, I didn't see your slides. Are there
Yeah.
implications on that? Okay, for the black hole, as an axion is a scalar field, so that it is possible to think that the axion as like Hawking radiation is maybe
It's
can
yeah. I mean, I think that's the first motivation for doing the super radiance. I think, yeah, it's a form of radiation as well, right? So I don't see my slide. Yeah, but yeah.
so they treat the axion field as a field from as a Hawking radiation, right?
It's I mean, people try to think about that, but the main mechanism is more like a quantum mechanical equivalent of Schrodinger equation. Yeah. So in the I don't remember now because it's a long time. But the point is that you analyze the scalar field around the black hole, right? You get some bound state, and that thing, yeah, I don't really say we will do that soon. that thing can extract a lot of energy. Like it's basically try to think about it, putting a mirror in around the black hole and stuff like that. Yeah, and just produce a lot of resonance effect. Yeah, back and forth, and then to just explode. So that's a axion super radiance.
So how is different between axion field? Maybe other scalar field are exactly the same.
The Right. So if you think about the ALPs, right? So ALPs is just any pseudo-scalar field. So anything that has a pseudo-scalar property, that's called ALPs now, right? So because it's like so common now. But I would say that if you really want to call axion, you would get a shift symmetry. Yeah, you should at least have a shift symmetry to protect that from receiving a mass. And that's basically how you categorize between just a common scalar field and the pseudo-scalar field. So the pseudo-scalar field has a shift symmetry, and it's a pseudo-scalar particles. So you can use that. But in terms of the GR and stuff, no. It doesn't make any difference, yeah, except that the mass is low. That's it. Yeah.
Okay, if anyone else have any questions, I would like to say thank you for the speaker, Dr. Chakrit. Thank you very much for today's talk. It's very great to have you tell us about the axion. Thank you very much.
ขอบคุณครับ
To see you later.
ขอบคุณครับ see you later มันออกยังไงวะ